Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about this problem. So let's get started. Let's see this problem. We are given a number n and we have to count all the set bits from 0 to n. So let's understand this problem better with few examples. So let's say if n is equal to 5, then you have to consider binary representation of a number from 0 to 5. And then you have to count all the set bits in all the numbers. Here in case of 5, these are the binary representation of number 0 to 5, and in this there are 7 set bits 1, 2, 3, 4, 5, 6, 7. So the output is 7. If n is 4, these are the numbers with binary representation of a number, and here there are 5 set bits 1, 2, 3, 4, 5. So the output is 5. We have seen the variation of this problem in previous video. In that problem, we had to find count of set bits in a specific number. But in this problem, we have to count total set bits from 0 to number. It means if number is 12, then we have to count total set bits from 0 to 12. Got it? So I hope you understood this problem really well. So let's pause this video and think about an algorithm to solve this problem. So before we move on to efficient approach, let's see brute force approach first. So the idea of brute force approach is simple. So here are all the binary representation of a number from 0 to 12. And what we do in brute force approach, we simply run a loop from 0 to n. It means from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we cover all the numbers. And in each iteration, we are going to traverse the binary representation of each number. And we simply count number of set bits. Okay? To count the number of set bits, there are two approaches. One is the basic approach to count number of set bits. In this approach, we simply traverse from least significant bit to most significant bit. And we check in each iteration that if the bit is set or not. If bit is set, we increment our count. And the time complexity of this approach is going to be big O of n into b, where n is the number of iteration because we are traversing from 0 to 12, right? And in each iteration we are traversing number of bits. That's why the time complexity is big O of n into b. And there is one efficient approach to count number of set bits. And that approach is based on Brian-Cunningham's algorithm. So what we do in this approach, we simply pre-compute count of set bits in 8-bit numbers. And then we use these pre-computed values to count number of set bits in 32-bit numbers for all the numbers from 0 to n, right? So the time complexity of the pre-computation is going to be theta of 1. And our loop is going to run n times, right, for each number from 0 to n. And in each iteration we are doing n into theta 1 work. So the time complexity of this approach is going to be theta of n. Okay? So both the approaches I have discussed in detail in previous video. So that's why I am not going in detail of both the approaches. If you want to know about the approach, I highly recommend to watch the previous video and come back here and continue watching this video. So instead of discussing both the approach and applying it in brute force approach, let's move on to discuss efficient approach. So here we have observations to be made. So let's say I am only assuming 3 bits number as of now. So if we have 3 bits number, how many numbers are possible? It's simple. 2 to the power 3, that is equal to 8. So it means if we have 3 bits, 8 numbers are possible from 0 to 7. Okay? Here m is equal to 3. M means number of bits. Here you can see binary representation of all the numbers from 0 to 7. So when you observe the binary representation of numbers from 1 to 7, then you will realize that at position 1, you can see that 1 bit is alternating. Means 1 bit is 0 and second bit is 1. Then 0, then 1, then 0, then 1. And if you observe second position in the binary representation, you see that 2 bits are alternating bits. First 2 bits are 0, then 2, then 1, 1, then 0, 0, then 1, 1. And if you observe third position in the binary representation, you see that 4 bits are alternating. And if you observe third position in the binary representation, you will realize that there are 4 bits are alternating bits. It means 4 bits are 0 and then 4 bits are 1. And if you count ones in all the position, you see that there are 4 ones in each position. First position also you find there are 4 ones. In second position also you find there are 4 ones. And in third position also you find there are 4 ones. Right? And we can write 4 as 2 to the power 2. Right? Great. So if I want to know how many bits are there, then I can easily find it. How? As we can see that there are 2 to the power 2 bits are there in first position, in all the position. And how many positions are there? There are 3 positions. So can we do 2 to the power 2 into 3? Yes, obviously we can do. So we get 12. And you see that there are exactly 12 bits are set from 0 to 7. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So if I have to write the generalized formula to find the number of set bits from 0 to 7, how can I write? So we can simply write 2 to the power m minus 1 into m. And here m is equal to number of bits. Right? So now you can relate that 2 is equal to 3 minus 1. That's why it is equal to 2 to the power 2. And how many bits are there? M bits. Means 3 bits are there. So this formula is exactly same as this calculation. Right? So now we know that if we have a power of 2, in this case it is 8, then we can easily count the number of set bits if a number is power of 2. So far so clear. Please remember this because we are going to use this fact to solve this problem. So let's discuss the idea for efficient solution to solve this problem. So we know the fact that if we get number that is a power of 2, then we can easily calculate number of set bits using this formula 2 to the power m minus 1 into m. Right? Now here let's say n is equal to 12. So I have written the binary representation of all the numbers from 0 to 12. Right? Okay. Moving on. So from 0 to 12, let's find the power of 2. So here 2 is a power of 2, 4 is also a power of 2 and 8 is also power of 2. Okay. So let's consider highest power of 2. And why I am considering highest power of 2? Because if we are able to find number of set bits in the highest power, then why would I take lowest power, right? That's the simple reason. So highest power of 2 is 8. So it means we can find number of set bits from 0 to 7. Okay. So here m is equal to 3 because 8 is equal to 2 to the power 3. So m comes out to be 3. So after putting the value of m into our formula, we get 12. So till 7, there are 12 set bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Correct? So far so clear. Now consider all the numbers from 8 to 12. If you observe this number carefully, there are 1 on the 4th position in all the numbers. And if you remove this number, it comes out to be this. And this binary representation is exactly same as 0, 1, 2, 3, 4. And if we apply the same formula for this number, we can easily count the number of bits because 4 is the power of 2. Okay? I will come on this point in a bit. So first of all, let's consider this number from 8 to 12 and count number of set bits on the last position from 8 to 9. So how can we count this? It's simple. What we do n minus 2 to the power, we do n minus 2 to the power m plus 1. N is what? N is 12. 2 to the power m is what? 2 to the power 3 is equal to 8 plus 1. So we get 12 minus 8, that is equal to 4 plus 1, 5. So this is how we count all the set bits from 8 to 12. Okay. Now let's remove all the bits. So our problem reduces to this. And this is exactly same as 1, 2, 3, 4. And now we have to solve this. And now we have to solve only this small problem. So what we do? We simply repeat step number 1 to find the highest power and get the number of set bits for n equal to 4. Because now there are only 4 elements left here. So we are simply repeating the step 1 to count the total number of set bits. Clear? So you might have guessed here that we are repeating a step here. It means somewhere we are using recursion. So you are absolutely correct. We are going to use recursion to solve this problem. And if you remember recursion from the previous video, what we care about in recursion? We care about only two things. First thing is what list amount of work we can do, and the base condition of the recursion. So in this solution, the base condition is simple. If our n reduces to 0, we simply stop and return. So this is the base condition. So I hope this idea of efficient solution is clear to you. Now let's move on to see the implementation of this efficient approach. So this is the efficient approach we talked about. So here we have a function count total set bits, and this function is taking n as input. The first if condition is our base condition, where we are checking if n is equal to 0, then simply returns 0. Okay. After if condition, we are counting the power of 2, highest power of 2, right? And as you can see in this code, I have used a left shift operator so many times. So let's first understand what this left shift operator is doing here. And what is one left shift something? Okay. As we know that 1 is equal to 2 to the power 0, right? Because 2 to the power is equal to 1. And if you see the binary representation of number 1, you see that it is 0, 0, 0, 1. And here each bit is representing power of 2. Okay. So 0, 0, 0, 1 means it is by default 2 to the power 0. Okay. And if I left shift 1 by 0, nothing is going to happen. It remains as it is. But if I left shift 1 by 1 position, then now this bit is shifted to second position. And this second position corresponds to 2 to the power 1. It means 2. And if I left shift 1 by 2 position, then now this bit is shifted to this position, and this position corresponds to 2 to the power 2, that is equal to 4. So it is simply a short way to find power of 2, right? That is why I have used left shift operator over here, and it is much faster than arithmetic operators. So this is about left shift operator. Now let's understand how the count highest power of 2 function is working. Okay. So when you call count highest power of 2, we initialize a variable power to 0 and we begin the loop. And in each iteration we are checking if the current power of 2 is less than equal to n or not. If it is less than equal to n, we are simply incrementing the power. Okay. And the execution of this loop continues until the power of 2 is less than equal to n. Okay. So let's see. Currently the power of 2 is 2 to the power 0, because 1 is equal to 2 to the power 0. 2 to the power 0 is equal to 1. That is equal to less than n. And in this case our n is 12. Then we increment the power by 2. So it becomes 2 to the power 1. This is equal to 2. It is also less than 12. Then we increment power by 1. So it becomes 2 to the power 3. 2 to the power 3 is 8. That is also less than equal to 12. And then it becomes 2 to the power 4 in next iteration. And 2 to the power 4 is 16. That is greater than 12. So this loop stops here and we simply return power minus 1. It means 4 minus 1, that is equal to 3. So this is how this count highest power of 2 function works. Alright, so we know how count highest power of 2 function works. So let's quickly dry run this code and see how it works. So when we call this function, the first line checks if n is equal to 0 or not. In this case, n is not equal to 0 because the value of n is 12. Okay. The next step is counting the highest power of 2. In this case, the highest power comes out to be 3. Correct? In next step, we are doing 1 left shift m minus 1 into m, and that is equal to 2 to the power m minus 1 into m. And this step corresponds to this step. Okay? Cool. In second step, we are calculating the value of b. And what is b? B is simply n minus 2 to the power m plus 1. And this step corresponds to this step. So in this step, what we were doing? We are counting the remaining set bits after 7 to 12, right? Okay. So after calculating the value of a and b, we are simply making a recursive call to this function by passing value of n. And what is this n minus 2 to the power m? This expression corresponds to, so this expression corresponds to this expression, right? Here we are reducing n, and we are again calling the same function for smaller value of n. This is what we are doing, okay? And at the last, we are doing a plus b plus c and return. So let's say if we call this function for value 12, so this function first going to calculate the value of m, it comes out to be 3, m is what? The highest power of 2. Then we calculate value of a, it comes out to be 12, then b, it comes out to be 5, and c is equal to a recursive call to function with the value 4, because n minus 2 to the power m is equal to 4. This recursive function calls, so this recursive function again start its execution from here. It checks if n is equal to 0, no, 4 is not equal to 0. So it calculates value of m is equal to 2, then it calculates value of a and b, and again it's going to make a call to itself recursively. So this time the value of n reduces to 0. And when this function calls f of 0, we hit the base condition where n is equal to 0, and it simply returns. So this function returns 0 to its parent, okay? So its parent calculate 4 plus 1 plus 0, means a plus b plus c, that is equal to 5, and returns value to its caller. Its caller is f of 12. What f of 12 does? It simply calculates value of a plus b plus c. A is 12, b is 5, and the value of c is 5. So 12 plus 5 plus 5 is equal to 22. So it means there are 22 set bits from 0 to 12. Alright. Now talking about the time complexity of this function. So whenever we have recursive solution, we generally write recurrence relation of the function to calculate time complexity. So the recurrence relation of this function is going to be time taken by this function is equal to, so we are doing some log n work here. So the count highest power of 2 takes log n time to get the power of 2, highest power of 2. Then we are calculating a, and that is a constant work. So that's why plus theta 1. And again we are doing constant work to calculate b, that is also a theta work. And then we are making a recursive call to itself by passing n minus 2 to the power m. Okay, so this is a complex recurrence relation of this function. So this is a complex, that's why it's a little bit difficult to calculate the exact bound. So that's why we are going to use our friend big O notation to find the upper bound of this function. So whenever we are unsure or unclear about anything, we use big O notation to find the upper bound of a function or an algorithm. So here the upper bound of this function comes out to be big O of log of n. As you can see that if the n is 1, we are only going to make 2 recursive calls. One for f of 4 and one is for f of 0. Okay. Now we cannot ignore space complexity because it is a recursive solution, and we know that whenever we write recursive solution, we need space on function call stack to store all the recursive function calls. So in this solution, we need big of log n stack frames to store all the function calls on a function call stack, right? So far so clear. So in this solution, the time complexity comes out to be big of log n, and the space complexity comes out to be big of log n. So in next video, we are going to optimize this, and we are going to solve this problem in much better way, that the space complexity comes out to be theta of 1. It means we are going to solve this problem in constant space. I highly recommend to watch that video also. Okay. So far so clear. So let's have a quick recap of what we have done so far. So we are given a problem to count total number of set bits from 0 to n. So to solve this problem, we saw the brute force approach, and in brute force approach, we saw the 2 approaches to solve this problem. The first approach took big of n into b time to solve this problem, and the second approach took big of n time to solve this problem. I have discussed both the approaches in previous video. So if you have not watched that video, then I highly recommend to watch that video first. Okay. to better understand this problem. And the next approach we saw is the efficient approach. In efficient approach, we simply break the entire problem into smaller subproblem and we use recursion to solve this problem. So the time complexity of this efficient solution comes out to be big O of log of n, and the space complexity comes out to be big O of log of n. In next video, we are going to solve this problem in more efficient way, where we are going to solve this problem in space complexity theta of 1, means constant space. So please watch that video also. So this is it for this video. Thanks for watching. See you in the next video.